Everyone, I am Yanami Copio, BSc CA3 student of ISAT University, and this is ECE23 Performance Task number 10. So I will be discussing about the Synchronous Optical Network, or Sonnet. So Sonnet defines a technology for carrying many signals of different capacities through a synchronous, flexible optical hierarchy. It encodes bit streams into optical signals propagated over optical fiber, and all clocks in the networks are locked to a common master clock so that simple TDM can be used. The Sonnet multiplexing is done by a byte interleaved, and so the transmission links of the telephone network have been changing to Sonnet, where rates are arranged in STS, or Synchronous Transport Signal Hierarchy. So the first step in Sonnet multiplexing process involves the generation of the lowest base signal, and this base signal is called the Synchronous Transport Signal Level 1, or STS1, and this operates in 51.84 Mbps. So I have here the table for the Sonnet hierarchy, and so for the higher level signal, for example, we have STS3. So it will be the integer multiple of the STS1, which is the 51.84 Mbps multiplied into 3, so that totals to equals to 155.52 Mbps. So this creates the family of STSN signals, where it is composed of a n-byte interleaved STS1 signal. So this table also includes the optical counterpart for each STSN signal, which is the designated optical carrier level N, or also called OCN. So we have here the table. So for STS1, its counterpart for optical carrier 1 is this, and the capacity is 28 digital signal, or 1 digital signal. That's so for 28, that is for the level 1, and for the 1 digital signal, that is for the level 3. And also for the rest of the level, or STSN family, these are their designated bit rate and their capacity. So let's proceed in the frame format or structure of Sonnet. So Sonnet uses a basic rate of STS1 that is equal to 51.84 Mbps. So STS1 is a specific sequence of 810 bytes, which includes various overhead bytes and envelope capacity for transporting payloads. And payload is a revenue producing traffic being transported and routed over the Sonnet network. So we come up for 810 bytes because we have here a 9 column and 9 rows and 90 column. So its frame length is about 125 microsecond, and which totals for 8,000 frames per second. So the order of transmission of byte is by row, from top to bottom and from left to right, which from the most significant bit first. So the synchronous payload envelope over here can be divided into two parts, which is the STS path overload, or the POH, and the payload. So once the payload is multiplexed into the synchronous payload envelope, or SPE, it will be transported and switched through the Sonnet without having to be examined and possibly demultiplexed or at intermediate nodes. Thus, Sonnet is said to be service independent or transparent. So transport overhead in this part is composed of section overhead and line overhead. So the STS1 POH is part of the synchronous payload envelope. So the STS1 payload envelope has the capacity to transport up 28 digital signal on the first level, 1 digital signal on the third level, and 212.048 Mbps signals, and the combination of each. So the frame elements is consist of an overhead or transport overhead and plus an SPE or the synchronous payload envelope. So the first three columns on this part is um, make up. So the first three columns on this part of each STS1 frame is made up of the transport overhead. And on the last 88 columns on this part, from this part, is made up of the SPE. So the envelope capacity in the synchronous payload envelope. So in this figure, the SPE occupies the STS1 envelope capacity. So the STS1 SPE consists of 783 bytes. So this 87 columns will be multiplied into 9 rows, so that's 783 bytes. And the column 1 contains 9 bytes designated for the STS1 POH or path overhead, and the next two columns are this 30 and 59 are not used for payload but are designated as the fixed stuff column. So the remaining 756 bytes in the remaining 84 columns are designated as the STS1 payload capacity. So we have here the STSN frame structure. So the STSN is a specific sequence of n times 810 bytes. So that's formed by a byte interleaving STS1. So STSN is formed by a byte interleaving of STS1. So the transport overhead of individual STS1 are frame aligned before interleaving, but the associated STS SPEs are not required to be aligned. It is because STS1 has payload pointer to indicate the location of the SPE. So let's proceed to the Sonnet multiplexing. Sonnet multiplexing has, these are the principles for Sonnet multiplexing. We have four principles, that is the mapping. It is used when tributaries are adapted into VTs by adding justification bits and POH information. And next is the aligning, which takes place when a pointer is included in the STS path to allow the first byte of the VT to be located. And multiplexing is used when multiple lower order path layer signals are adapted into a higher order path signal, or when a higher order path signals are adapted into the line overhead. And the last is the stuffing, which the Sonnet has the ability to handle various input tributaries rates from the asynchronous signals. So next is the Sonnet network configurations. We have the simplest Sonnet configuration. This is the point-to-point configuration. It involves two terminal multiplexers linked by fiber with or without a regenerator in the link. So the Sonnet path and the service path are the digital signal 1 or digital signal 3 level 3 links and are identical, and this synchronous island can exist within an asynchronous network world. So next is the point-to-point configuration. So it is also called a linear adder drop. So it includes adding and dropping circuits along the way. And Sonnet ADM or add drop multiplexer is a unique network element designed for this configuration. It avoids the current of demultiplexing, cross-connecting, adding or dropping channels, and then remultiplexing. So the ATM is typically placed along the Sonnet link to facilitate adding and dropping tributaries channels into the intermediate points in the network. So next is the hub network configuration. So hub network configuration accommodate unexpected growth and change more easily than simple point-to-point networks. So so number one, using two or more ADMs is a wideband cross-connect switch which allows cross-connecting the tributary services at the tributary levels. And the second one is using a broadband digital cross-connecting switch which allows cross-connecting at both the sonnet level and the tributary level. So the hub concentrates traffic at a central site and allows easy reprovising of the circuit. And so the last network configuration is the ring architecture or the ring configuration, and this is the building block for ring architecture is the ADM. So multiple ADMs can be put into a ring configuration for either bidirectional or unidirectional traffic. So the main advantage of the ring configuration is its survivability. So if a cable is cut, the multiplexers can have the intelligence to send the services affected via an alternate path through the ring without interruption. So that's the end for my presentation for ECE 23 performance task number 10. Good. Thank you.